Okay, welcome once again to our course. So to continue our lecture, so we will have more NumPy multiplication. So I already imported the NumPy here as NP. So I already executed the code here. So we'll be continuing and building our lecture from the previous one. So I would like to again to give more examples on NumPy matrix multiplication. And I want you to understand the operations in NumPy multiplication. Even though we're using here a library that automatically computes, but I think it's important also that you understand how to multiply manually so that you will appreciate more this NumPy, how this one is a lifesaver. It's a very lifesaver. So for example, I would define let's say a 2 by 2 matrix. So again, A is equivalent to NP dot array. So I'll define 2 by 2 matrix. So we have 2, 3, -5, 4. So don't forget the piping it in the list. Create a matrix. So we have reshape. So 2 by 2. So another matrix, let's say a 2 by 2 matrix. So NP array. Then we have 3, -2, 1, and 6. So we will also reshape this. So 2 by 2. Of course, we have 4 items. So let me alt enter. So let's see. This is the A. So 2, 3, -5, 4. So this is the B. So 3, -2, 1, 6. So although we can automatically here get the answer, so I want to explain how we derive this 9, 14, 11, and 34. So again, this time I will use the annotate.net. If you want to have this one, this is a free tool. You only have to register. So for example, again, we have 2, 3, -5, 4, 3, -2, 1, 6. So let's compute this in another tab. Okay, so I will choose the red color first. So we have this one. We have this matrix. So sorry for the bad handwriting. I'm not much of a calligrapher. So for example, 2, 3. So we have -4. 5. 4. So we multiply this 2 by 2 array with another 2 by 2. This time this is a matrix already. So -2. So 1 and 6. So normally you will do this. So this is a 2 by 2 to check if we can multiply this one. So if the inner one corresponds or they are the same, so we can multiply this one. They're the same size. Then our output again will be a 2 by 2 matrix also. So we'll be expecting this one. So the result will also be a 2 by 2. So we'll provide the answer for that. Okay. So what you will do here is to multiply the 2 against the 3 and the 3. So let me have another color. And the 3 against the 1. Okay. So that's the pattern. So -5. So -2. So let's say black one. So we have 4 and 6. So that's what we will do. So let's do the operation. So I'll select this green. So we have 2 times 3. So plus we have 3 times 1. So 3 times 1. So this will be the result for this one. So we have also, let's do this second one. So we have 2 times -2. So plus 3 times 6. So this one, so 3 times 6. Okay. to another row, which is negative 5 times 3. So plus we have 4 times 1. Okay, so the next, so we have negative 5. So this negative 5 times negative 2. Okay, so negative 2. So plus we have this 4 times 6. So we have this 4 multiplied by 6. Okay, so let's derive the answers. So this is 6 plus 3. So this is 9. So we have negative 15 plus 4. So this will be negative 11. Okay. So we have here negative 4 plus 18. So we have positive 14. So we have the positive 10 plus 24. So we will have 34. So the answer will be 9, negative 11. So we have 14 and we have 34. So as you can see, 9, negative 11, 14, 34. Okay, so we have 9, 14, negative 11, 34. Okay, so this will be the final answer. So I hope you appreciate more the NumPy library, because if you want to compute this manually, you will have to do this all. Okay, imagine if this is a big matrix. So we will have a lot more of computation here. So again, 9, negative 11, 14, 34 to check. So 9, negative 11, 14, 34. We have the correct answer for the matrix multiplication. So again, I want to highlight, we will use dot and not multiply. So NumPy also has the multiply. So for example, np dot multiply. So let's multiply. This is an element-wise multiplication. So this is not the real matrix multiplication. It's just multiplying each element. So let me comment on this, so that you will not be confused. So this is different. So multiplication element wise only. So you only multiply by element. So for example, you have 3 times, I think 2 times 3, so that's 6. So you have 3 times negative 2, so negative 6. So this is not the real matrix multiplication. Okay, so you will use the dot. Also, as an alternative, you can also use this one. So np dot math multiplication matrix, I mean. So you have also, for example, we have AB. So this means instead of a dot, we're using here matrix multiplication. So I'm hoping for same result. Okay, so this one. So I would like to highlight this one. So if you're using dot, it's okay. If you're using math multiplication, so remember we have the same answer. But definitely if you're doing matrix multiplication, you will not use this one. Okay, this is wrong in terms of matrix multiplication, but in terms of element-wise multiplication only, such as, for example, scalar multiplication, this will do. Okay, so let's have another example. Let's have for example, a 2 by 3 or by multiplied it by 3 by 3 matrix. So I hope you will appreciate more of the NumPy library. So let us have another example. So let me first clear this one. So we clear the annotation. Okay, so how about we have, for example, another NumPy array. Let's multiply, for example, a 2 by 3 matrix by, how about 3 by 3 matrix. So for example, we have C, we denote C. So again, np array, so we'll create a 2 by 3 matrix. So composed of the following values. So 2, 3, 1, 2, -7, and 4. So then we will reshape this one. So 2 by 3. So another matrix or the multidimensional array. So let's create a 3 by 3 array here. So 3, 4, 5, 1, 1, 4, 2, 1, 4. So this is a 3 by 3. 1, 2, 3, 4, 5, 6, 7, 8, 9. So this qualifies, will be qualified as a 3 by 3 array when we reshape this one. So reshape 3 by 3. So shift enter. So let's see. So this is C. So enter. So 231, 274. So let's, for example, this is D. So this one is 345114214. So before we execute the np dot dot so cmd. So let's try to compute this one first manually so that you would understand more. So again, we have here the annotate. So let me just move this one. Oh, I'm sorry, I'm in the pen mode. Okay, so let me clear that first. So I'll click the arrow. Okay, so let me drag this one up. So we have the following values. So 231, 274, 345, 114, 215. Okay, so let's compute that one. So if we have this, so let's denote this is C. Okay, we have array C, which is 2, 3, 1, 2, -7, then 4. Okay, I have some notes here. It's written on paper. Okay, this is just a simulation. So 3, 4, 5, then 1, 1, 4, then we have 2, 1, 4. Okay, so what will be the product here? So again, you test if this one can be multiplied. So this is a 2 by 3. Okay, 2 rows, 3 columns. So this is a 3 column and 3 rows. Okay, so can we multiply this one? Yes. So if this one again is the same, so it means we can multiply this one. Then the result will be having a 2 by 3 matrix. So we're expecting this one. So we have 2 rows and then we have 3 columns. So for example, 1, 2, 3. So we are expecting 6 numbers here. Okay, so let's try to compute. Okay, so let me have the black one. So you multiply this one with this one. So 3 by this one. So 1 by this one. So another one. So you 2 times 4. Then 3 times 1. Then 3 times 1. Okay, so let me undo that. So let me clear. So another one, you multiply this one. So 5. Okay, I'm sorry. So 2 times 5. Okay, so you multiply this one. So 5, then 3, 4, then 1, 4. Okay, so let's do that now. So let me just undo it. Okay, so I'll select the green. Okay, so we will have 2 times 3 plus 3 times 1. So plus 1 times 2. Okay, so next one, so we will have 2 times 4 plus 3 times 1 plus 1 times 1. Okay, so let me zoom out, zoom in. Okay, so that I will have more space. So next one we have 2 times 5. So 2 times 5 plus 3 times 4 plus 1 times 4. Okay, so second row. So we will have 2 times 3 again plus negative 7 times 1. So plus 4 times 2. And next, we will have 2 times 4, negative 7 times 1. So we have 2 times 4 plus negative 7 times 1. So we will have 4 plus 1. Okay, so let me zoom out again. So this is the last one. So we'll have 2 times 5 plus negative 7 times 4. So plus, we have 4 times 4. So let's complete the operation. So we have 6 plus 3, okay, plus 2. Okay, so that is 11. Okay, so we have here 8 plus 3 plus 1. So we have 12 here. So we have 10 plus 12 plus 4. So we will have 26. So again, 6 minus 7. Okay, so 6 minus 7 plus 8. So we will have positive 7. So 8 minus 7, okay, plus 4. So it's 5. So this is 10 minus 28, negative 18 plus 4 times 4. So this will be negative 2. So our answer, so let me zoom this in again. So our answer will be 11, 12, 26. So this will be 7, 5, and we have negative 3. Okay, so let us execute this one in Python. So I hope you're appreciating more the NumPy library, because again, if you will do this manually, it's possible to do this manually, but look at the time that you will spend. Okay, so let's do that. So let's execute this one. So Alt, Enter. We have 11, 12, 26, 7, 5, negative 2. So let's confirm. So 11, 12, 26, 7, 5, negative 2. So it's the same. So this will be our answer. Okay, 11, 12, 26, 7, 5, negative 2. So let's see our manual computation. So 11, 12, 26, 7, 5, negative 2. So far so good. So I hope you're appreciating, I'm emphasizing here, I hope you're appreciating the NumPy library. So if you do this manually, imagine if I have a 4 by 4 matrix or 5 by 5 matrix or 6 by 6. Imagine the number of steps you will do. Okay, so let me clear this one out. So for the next section, we will have the transpose of a matrix. So a transpose of a matrix in linear algebra is an operator which flips a matrix over its diagonal. It switches rows and columns. That's the only bottom line here. Bottom line, uh, column indices of matrix A by producing another matrix, often denoted by a with a superscript of P. So how can you do the transposition of a matrix? So I think this one is very easy. So for example, now let me write this one. So for example, you have a matrix this. I will write this on this directly. So for example, you have 1, 2, 3, 4. Okay. So what would be the transpose of a matrix here? So A. So what would be a transpose? So you just switch the row into columns. So the result of this one, so A sub T, no sub, superscript, okay, A to the T. So you have 1, 2, and then you have 3, 4. Okay, so this is the transpose of a matrix. Okay, we will not spend much time here because this concept is self-explanatory. So let's just test this one. Okay, so how about matrix P, for example, equals np dot array. So we have 1, 2, 3, 4. Okay, so reshape this one into 2 by 2. So Alt Enter. So how can you find the transposition of the matrix? So again, you use NumPy, but this time you use the extension of alg. Then you will use the transpose function. Okay, so we have here matrix T. So the result of this one. So wait a minute, I think I made a mistake here. So linear algebra. So let's test this first. So NP, I think it's not part of the linear algebra. Okay, so we go directly with transpose. I think, yeah, I'm sure. So Alt Enter. So this is the transposition of the matrix. So sorry about the error. Sometimes my mind gets clouded. What is a function or what is a method? Okay, so np.transpose of the matrix, as you can see, from 1, 2, 3, 4. Okay, so the result is 1, 2, 3, 4. But the row and column switches already. Okay, so you can do also this one. Okay, so how about we generate more matrix? So let's say matrix F equivalent to NP. Let's use arrange. So we generate number from 1 to 6. Then we will reshape this one into 2 by 3. Okay, so let me just remove this one. Let's clear this one. So shift enter. So if you want to see matrix F, okay, so that is 1, 2, 3. So 2 rows, 3 columns. So let's transpose this one. So transpose, this is matrix F. So the result is just the row becomes now the column. Okay, so 1, 2, 3. So 1, 2, 3, 4, 5, 6. So that is just the concept of transposing a matrix. Okay, so the next one will be the determinant. Okay, so determinant in linear algebra is a scalar value that can be computed from the elements of a square matrix. So the requirements for uh, computing the determinant will be a square matrix, meaning same size of rows and columns. And it encodes certain properties of linear transformation described by the matrix. So it's denoted by matrix A, okay, denoted by determinant A without the parenthesis or the pipe. It looks like the absolute value of a determinant. So for the next line here, we will encode some examples. And now we'll show you how to compute the determinant both manually and using the NumPy library so that you will appreciate more. So let me just save this first one. So let us continue. So let me demonstrate to you how to use the determinant in NumPy. Then after we derive the answers, I'll do it manually so that you will appreciate more. So for example, I have a bet A, so find the determinant. So again, I will define a matrix. So remember, determinant can only be given, or this is only possible for a square matrix. Okay, so NP array. So let's have a simple array. So 1, 2, 3, 4. You can do this with NP arrange too. So let's do that. So NP arrange. So generate from 1 to 5. Okay. Then we restate. So we have a 2 by 2 matrix. So NP dot arrange. I'm sorry. Okay. So we have determinant A. So this is not the determinant so far. It's just the matrix. So again, 1, 2, 3, 4. Okay. So how we find the determinant? So NP. So now we will use the linear algebra, okay, library as part of the NumPy. So we will use DET for that determinant. Then we'll pass on the matrix, which is a 2 by 2 square matrix. So shift enter. So our determinant is -2. So never mind the long decimal. So this is -2. So how do we derive that -2? So again, let me use again this annotate. So let me just zoom out. Let me just drag this one. Okay. So if you have time, you explore this annotate.net if you're presenting in class or as an instructor. So this is a very good tool for uh, a whiteboard or a blackboard. Okay. So how do we derive the determinant first? So let me have a pen here. So the general formula, if we have a 2 by 2 square matrix, so we have the determinant of A. If we have a 2 by 2 square matrix, so let's denote this one as A, B, C, D. So we have here a square matrix 2 by 2. So you derive this by multiplying A and B. So this will be AB minus the B and C. Okay, it's the cross. So this one is B and C. So remember our given. So we have 1, 2, 3, 4. So remember. So we're expecting here an answer of -2. So we have 1 times 4. So remember that. So 1 times 4 minus 3 times 2. Or 2 times 3 anyway. It's just a multiplication. So let me correct this. Okay. So let's follow the order. So this one is BC. So this one is 2 times 3. Okay. So this one is 4 minus 6. So our determinant will be the -2. Okay. So this one is -2. So in our NumPy, we use linear algebra for the determinant is -2. So that's how you compute the determinant. But what if we have a 3 by 3 matrix? So for example, so we have these given. So for example, we have how about determinant B equivalent to, for example, let's create a array, probably 3 by 3. So we are requiring square matrix only. So 5, 3, 7. I'm randomly choosing values here. So 5, 8, -6, 4, 9. Then we reshape this again. Yeah. So 3 by 2. I'm sorry, that cold, but it's not COVID, by the way. Okay, so we reshape this one. So that B. So let's see the value. So 5, 3, 7 to -5, -6.9. Okay, so let's find the determinant of B. Okay, so let's directly use the NP dot linear algebra of determinant. Lin ALG, okay, linear algebra determinant of B. So our answer is negative 737 at least. So how can you do that manually? Okay, so how can you do that manually so that you will appreciate this more? So let's grab this one. Okay, so that we have a very clear board. So again, I'll use the red one. So you find the determinant. So let me explain. Okay, for a 3 by 3 matrix. So assuming you have A1, you have B1, C1, you have A2, B2, and C2. So you have also A3, B3, and C3. Okay. So what will be determinant? The determinant of that one is this one. So you place a reference. So A1. So you multiply this one. So if I will cover this one, so our reference is A1. Okay, so never mind this one for now. Okay, so you will have B2, C2, B3, and C3. So remember, this is already a 2 by 2 square matrix. So you have a formula of AB minus BC. So minus. So we just alternate this one. So this one is positive, negative, positive, negative, positive, negative. Okay, so you just alternate this one. So we have minus. So let me erase this first so that we have a clean board. So I'll erase this one, including this one. Okay, so let's erase. Okay, so erase this one. Then let's bring it back. So this one is C1. So this one is B2. This one is A3. So we have minus. So assuming your reference now is B1. Okay, so imagine you have a pencil and you try to um, place the pencil above. So you will have this one. So you have B1. Okay, so you multiply by A2, C2, A3, and C3. Okay, so the next one, so this will be plus. So again, imagine you have a reference of C1. Okay, so imagine you have a reference of C1. So this one is C1. Okay, imagine that. So this one is C1. So you multiply this one by A2, B2. So you have A3 and B3. Okay, that's how you will find the determinant for a 3 by 3 matrix. So for example, so let's solve based on our given. So this one is 5, 3, 7. Okay, so let me correct this one. This one is 7 and 2. So we have negative 5, 8. So negative 6, 4, 9. Okay, let's do this one. So our A1 is 5. So 5. Um, so again, so how will you compute this one? So again, if you remember for the, so let me remind you, I think it's still up. Okay, so if you have a 2 by 2 matrix, your formula for the determinant is AB minus BC. But since we have 3 by 3, okay, we can go directly for the formula as we have need to assign reference points. Okay, so this one, B2 minus B2 times C3. Okay, so B2 times C3. So if you have this one, so this one is negative 5 times 9. Okay, so that will be 45. So I will go directly here. Okay, so negative 5 times 9 is negative 45. Okay, so minus, so 8 times 4. 8 times 4, this one is 32. So my B1 is negative 3. Okay, negative 3. So we multiply A2. Okay, A2 to C3. So this one is 18. Okay, 18 minus 48. So that will be plus. So this one will be 66. Okay, and I'm going directly here, not showing the other operation. Okay, and next one, so plus, we have C1, which is 7. So I got A2 and B3. Okay, so this one is 8. 8 minus 30. Okay, so this one is 8 minus 30. So we have 5 negative 77. So minus 3 times 66. Okay, so plus 7 minus 22. So if you're computing this one, so negative 7 multiplied by 5, so negative 385. So minus 198. So this one is minus 154. So let me zoom out. So if you do that, so we will arrive at negative 737. Okay, so we have 737. So let me erase this one. Okay, so we have 737. So negative 737, so our determinant is negative 736.999. So I don't know why Python has a decimal point. Okay, but theoretically this is negative 737. Okay, so we have the same answer. So far so good. So the next one is how about we inverse the matrix. So the next one is inverse of a matrix. Okay, so what is inverse of a matrix? So the concept of inverse of a matrix is a multi-dimensional generalization of the concept of reciprocal of a number. The product between a number and its reciprocal is equal to 1. The product between a square matrix and its inverse is equal to the identity matrix. Okay, so we just find the inverse of a matrix. So if you have recalled, so for example, okay, so we have a number 6. So what is the reciprocal? So 1 over 6. So matrix also has that concept that if you multiply the original by its inverse matrix, you will arrive at the identity matrix. Remember the I function that we used to uh, execute previously. So again, let me remind you uh, of the identity matrix. So for example, you have this one. So np dot I. So now you have 3 by 3 identity matrix. So this is an identity matrix. Why? So in diagonal we have all ones, then the upper and lower we have a 0. So it just means that if you multiply the original by its inverse matrix value, you will arrive at this identity matrix. Okay, so let me just demonstrate this one. So let's remove this one. Okay, so let us first remove this one. So let's clear the screen. So for the identity matrix, okay, So again, we'll just before I execute this one, so let me discuss first what is an identity matrix. Okay, so we have the identity matrix, so denoted by this one. So for example, I have matrix A, and I have a simple value, a 2 by 2 matrix of 2. We have, and then we have 5. So 1, 3. Okay. So what will be the denoted by 3 to the negative 1? So what will be the inverse matrix of this one? So for the inverse matrix of a 2 by 2 matrix, so it's just easy. But let me explain. Okay. So a to the negative 1, which is the inverse. So the formula for this one is 1 over the value of its determinant. So multiply by the adjunct. Okay, so I'm writing here by the, not adjunct, sorry about that, adjoint. Okay, so this will be the adjoint of A. Okay, so what will be the our uh, determinant first? So to compute the determinant again, so you know that computation for the determinant for a 2 by 2 matrix. So this one is AB minus BC. So this one is 3, okay, times 2 minus 1 times 5 is 5. Let me write this one. So this one is, so this one is 5 times 1. Okay, so that's 5 times 1. So this is 6 minus 5. So our determinant will be 1. So we'll be using this here. So how do you compute for the adjoint? So let's use the cofactor method. Okay. So for example, so let's derive the cofactor of 2 first. For example, let me have the green color. So how about this one? So I will derive this 2. This one 2. So its cofactor is, if you remember your linear algebra. Okay. So this one is negative 1 raised to the power of the number of row, okay, the nth row plus the nth column. So Rn plus Cn. So let me explain that. So this one is row 1. So let me have the black one. So this one is row 1, this one is row 2, this one is column 1, this one is column 2. So Rn plus Cn. So this one, the 2, you will find the number 2 at row 1, column 1. So this one is, so 1. Okay, so let me erase this. So this one is, see, I'm such a bad writing. My writing is bad. So this one is 1 plus 1. Okay, so 1 plus 1 because we have 2. So what will be our adjoint number here? Okay, so our adjoint here, so if you notice this again, I'm using 2 here. So imagine this one. So this will be 3. Okay, so this will be times 3, which is equivalent to 3. Okay, so negative 1 squared is 1, positive 1 times 3. Okay, so this one will be the 3 here. Okay, so next one. So let me erase this first. Let me write again. So this one is, I think this is 2. Okay, so let's find the cofactor for 5. So let's find 5. So for the cofactor for 5, we have a negative 1. So row, it's still row 1, but this one is column 2 already, so plus 2. So times, so imagine this one. So you will not be needing 3 and 2, so that is 1. Okay, so imagine this one. So you have 5. Okay, so this is 1. So I'll write this down. This will be 1. It's equivalent to negative 1. So times 1, this is negative 1. So again, let me erase. I hope you're getting the pattern. Okay, so let me rewrite again. So this is 2, 5. So again, let's derive the cofactor of 1 here. So we have 1. So again, negative 1. So we have row 2. So this one will be 2 plus 1. So times. So this one will be, I'm concerned with 1. Okay, so this one is 3. Okay. I think no, not 3. I'm sorry. So this one is 5. Okay. So if you look at this one, so we're concerned about here. So this one. Okay, so this one is 5. So this is 5. So it's equal to negative 1 times 5. This one is negative 5. Okay, so let me erase this one again. Okay, so last one. So let's find the cofactor for 3. Okay, so this one. So the cofactor for 3 is just the same. So negative 1. So we raise to the power of 2, row 2 plus column 2. So this one is 2 plus 2 times, so we're concerned with 3. So this one is 2. Okay, so this one is equivalent to 2. Okay, so if we write this down, so let me bring out. So we have found the cofactor for this one. So again, we're deriving here the inverse of a matrix. Okay, so what will be the result? So again, so this one is, the 3 is for the 2. So this one is 3. Okay, so the next one is for the 5. So this one is negative 1. Okay, so this one is for the 1. This 1. So the result is negative 5. Then lastly, we have 2. Okay, so are we finished now? So no. So the adjoint of A is just equivalent as the transpose of this matrix. So again, if you transpose this one, so you will result in 3. So negative 1, then you have negative 5, and then you have negative 2. Okay, so remember the transposition of a matrix is this one. So we're not done yet. This is the adjoint. Okay, so let me play this one. So this is the adjoint of A. Okay, so this one, the transpose of our cofactors. So if we apply the formula, so 1 over 1, so we multiplied by, this one is 3, so minus 5, so this one is negative 1 and 2. So 1 divided by 1 is 1, so you just distribute 1. This is a scalar multiplication. So our inverse of the matrix is 3, so negative 5, so negative 1, and 2. Okay, so let's confirm that by using the NumPy. So we have here the value of what are given. So 2513. Okay, So let's create this one. So inverse of A. So NumPy array. So we have 2, 5, 1, 3. Then we will reshape this one. So dot reshape. So this one is 2 by 2. Okay. So this one is 2 by 2. Then we find the inverse of the matrix. So NP, again, part of the linear algebra library is the inverse of a matrix. So this is invert A. Okay, you want to invert that one. So our result is 3, -5, -1, 2. So I think we got the correct answer if we after we have done it manually. Okay, so we have 3, -5, -1, 2. So 3, -5, -1, 2. So that is how you compute the inverse of a matrix for a 2 by 2 matrix. Okay, so how about a 3 by 3 matrix? So the process is still the same. Okay, so again, what is the concept of this one? So if I assign this one, so for example, I assign this one also in a variable. Okay, so shift enter. Okay, and I assign this one, let's see, I assign this one to original. So original A, so this one, okay. Then we have the inverse A, okay. So it says here that the product between the square matrix, the original, and its inverse must be equal to the identity matrix. So let's do that one, okay. So we have for example, we define a new matrix. So let's see the product here. So then np dot. So we have rig A, then we have inverted A. Okay. So let's see the result of the new matrix. So I'm expecting here this one is a identity matrix. So this new matrix is dot original. So this one is the inverted one. So it means that the product between a square matrix and its inverse is equal to the identity matrix. Okay, so np dot. So let's execute this one. So this one is the original. Then we have an error here. So this one is the original inverted. So we have a new matrix here. Okay, so I'm expecting the new matrix to be the, look at this one. I'm expecting this could be the identity matrix. So look at the diagonal, 1, 1, then we have 0, 0. So that's the concept of the inverse of a matrix. If you multiply the original one with its inverse, it will result to the identity matrix. Okay, so next example, let's try how about a 3 by 3, but definitely I will not try a 4 by 4 matrix because it's hard. Honestly, it's so hard. So for this example, I will just uh, show you an example of a 3 by 3 matrix. So for example, we have this one. So let's compute this one. For example, so let us have this one as 3 by 3 matrix. For example, so we have matrix. For example, matrix 3. Okay, denoted by 3 by 2. So for example, we have this example. So 2, -1, so 0, so 0, so 1, 1, 2, 1, 1, and 0. Then we reshape this one. Reshape to 3 by 3. Okay. Non-keyword argument. So again, I always forget the square brackets here. Okay. So again, let us execute again. So 3 by 3. So this one is our matrix 3. So this one will find here the inverse of this one. So 2, negative 1, 0, 0, 1, 2, 1, 1, 1. 1, 1, 0, I mean. Okay, so how can I find the inverse of a matrix? So again, let's do this manually. Okay, before we arrive at the answer. So for example, NP, so linear algebra dot inv. So this one is matrix 3. So I'll not execute this one. Let's see if we can derive it manually before we execute the NumPy equivalent for inverse of a matrix. So how will you do this one? Okay, so let's set aside this one. So we'll be doing a 3 by 3 matrix using our example. So for example, we have A, okay, so we have A, then we have the following given. So 2, so this one is negative 1, so this one is 0, this one is 0, so 1, this one is 2, so 1, 1, 0. Okay, so what will be the inverse of this specific matrix? Okay, so again, so you write the formula. So the inverse of the matrix is equivalent to 1 over the value of the determinant multiplied by its uh, adjoint. Okay, so let me write slowly. So the adjoint of A. So meaning, so our determinant must not be equivalent. So remember, to 0. So if our determinant is 0, so 1 over 0 is undefined. So if that is the case, if our determinant is 0, if 0, so the inverse, let's denote this as inv, the inverse does not exist if the value of determinant is 0. Okay, inverse does not, okay, so the inverse does not exist. That's not hot, huh? This one is not. Okay, if the value of our determinant is 0, then the inverse does not exist. Okay, so let me erase this one. Okay, so assuming that A is not equivalent to 0. Okay, so let me clear this one. Let me write it again. So A. Okay, so that will be the adjoint. So again, how will you find the determinant of this one? So from the previous example, we can find the determinant, okay, for a 3 by 3 by using this one. Okay, so we have 2. Okay, so we'll multiply this one by, so this one is 2. So 1 times, remember, if you're choosing this one, okay, so you set aside this first. So you look at this one. If you're choosing 2, you look at this one. And proceed again, if you remember, the formula or the determinant for a 2 by 2 matrix is AB minus BC. So this one is a 2 by 2 matrix, but we have also our reference which is 2. Okay, so let me do this one. So 2, so multiplied by 1 times 0 is 0, minus 2 times 1 which is negative 2. Okay, so we have next is minus, so why minus again? So we have the pattern here, so plus, minus, so plus. Okay, let me erase that one. Okay, next, green. color green. So the next one, so let me erase this one so that it will be clear to you. Okay, so we are selecting here this one, uh, the -1. Okay, so we're selecting here the -1. So imagine this one, exclude this one and exclude this one. Okay, so we have -1, then we have 0 times 0. Okay, that's AB, by the way. So 0 times 0 is 0 minus 2. So we multiply this one with -2. Okay, so plus. Okay, let me erase this again. Okay, so plus. So we're referencing here now is this 0. Okay, so any value multiplied by 0 is already 0. So right, so you don't have to do this anymore because the result will be 0. Okay, so let me erase this one. So our determinant, if we derive this one, so this one is -4 minus, okay, so this one is minus negative, by the way, this one is negative, okay, so -1, so this one is -2, okay, so wait, so this one is -1 times -2 is +2, so we have minus, okay, so this one is -2. So our value for our determinant is -6. So that's already the inverse. No, we find again the cofactors. So let me just zoom out. Okay. So we have a space here. So we'll find 9 cofactors. So let me have this one. So separate the lines here. So let's find first the cofactors for 2. So this one. Okay. So this one. So what is the cofactor for 2? So again, we have -1. Okay. So this is row 1, column 1. So means 1 plus 1. Okay. Times. So again, this one. So look at this one, this square. 1 times 0 is 0. So 2 times minus. Look at this one, AB minus BC. So again, look at this 2. So forget this one first. Okay. So we have 1 times 0 minus 2 times 1. So we multiply this one by -2. Okay. So it's equivalent to -2. So that is for the 2. So next one we have -1. So -1. Okay. So the same. So -1. We have 1 plus 2. So times. So we have -1 here. So 0 times 0, 0 times 0, then minus 2 times 1. So we have also here -2. So this one is equivalent also to so -1 times -2, which is the +2 already. So 1, this one is 1 to the third power, which is -1 times -2, which is +2. So next one we have this one 0. So we have this 0. So what is the cofactor? So this one is -1. Then we have 1, 1, row 1, so column 3. So this one is plus 3. Okay. So we have times, so if we have 0, we have 0 and -1. So times -1 equivalent to -1. That is just for the first row. So let me divide this one. Okay. So these are dots. Okay. So let me have this one. Separate this one. Okay. So these are for cofactors. Okay. So next one we have 0 again. So we have 0. This one, second row. Okay. So we have dot. So -1. Okay. So we have -1. So row 2. Okay. Row 2. Then we have column 1. So 2 plus 1. So multiplied by, if we select this one, to 0. So what remains, so for example, we select the 0. So what remains is -1 times 0. Okay. -1 times 0 is 0. Then 1 times 0 is 0. So we have here 0. Okay. Which is equivalent to 0. Okay. So another one. So let me erase this one again. Okay. So another one. We have 1 here. So 1. We have also -1. Always -1. As we're finding the inverse. Okay. Let me fix this one. So this is a plus. So this one is 2 plus 1. So we have -1 here. So this will be 2 row 2 plus column 2. So times. So we have 2 times 0. Okay, then 1 times 0 again, 0 again. So 0 is equivalent to 0. So the last one we have, the last for this row, so we have 2. Okay, so same. So this one is -1. So this one is row 2 plus column 3. Okay, so again, we're selecting this one. So let me just do this one. So you have 2 times 1 minus -1. Okay, so we have 2 minus -1. That will result to 2 plus 1. So we have here times 3. Okay, so -1 to the 5th power, that's odd. So it will result in negative. So this one is -3, by the way. Okay, so we have 3 more. So let me zoom out. Okay, so the same process, but for the last column. Okay, so I've erased this one. So let me just bring it back. So that's 2. Okay, so we have 1. So this one. So we have 1. So what will be the factor of 1? So cofactor. Okay, so I write this one. So we're finding here the cofactors. Sorry for the bad handwriting. Okay, so finding here the cofactors. So this one is -1. Okay, we have this one. So 1, this one, -1. So this one is row 3. So this one is 3 plus column 1. So this one is 3 plus 1. Okay, so times. So if we isolate this one, so we have this 1 times 2. So we have 2. Then 1 times 0 is 0 already. Okay, so we will have here negative 2. Okay, so this is a positive 1 times negative 2. So this one is will result to negative 2. So next we have 1 again. So we have 1. Okay, so if you're confused right now, you have to rewatch this video in order to find the pattern. Okay, so we have negative 1, always negative 1. So what is 1? So this one is row 3, column 2. So this one is row 3 plus we have a column 2. Okay, then we isolate this one. Okay, we have 2 times 2, which is 4. 0 minus 0 times 0. Okay, this is just AB minus BC. So we select this one. So imagine I have a pen here blocking this one. So we have this 4 values lang. So this is 2, 1, and 0, and 2. So 2 times 2 is 4, minus 0 is 4. So this one is times 4. Okay, is equivalent to this one is negative. Let me write this one again. So this one is negative. This one is odd. Okay, so negative 4. So last one, we have 0. So this one is 0. So we have 0. So what will be the factor? So this one is negative 1. So again, row 3, column 3. So this one is 3. Let me rewrite this again. Hard to write with a graphic tablet. So this one is 3. Okay, so plus 3. Okay, so we're here at the 0 here. So you isolate this one. Okay, so we have 2 times 1, which is AB. Okay, so 2 minus 0 is 2. So this one is times 2. This is even. This will be positive. So 1 times 2 is equivalent to 2. So we have the following cofactors. Negative 2, 2, negative 1, 0, 0, negative 3. Okay, so negative 2, negative 4, and 2. So how do we derive, okay, the adjoint? So we derive the adjoint by writing the cofactors. So this one is negative 2. Okay, this one is negative 2. Then the next one is for negative 1. I think this is 1. We have no negative 1. So this is 1. So this one will be 2. So the next one we have for 0 is 0. Okay, so this one is negative 1. So let me rewrite this one. We have 0. We have 0. We have negative 3. Okay, so let me erase this one. I don't have a negative 1 right here. I think this is 1 or negative 1. Okay, I think I have the wrong given. So I think this one is negative 1. So again, so this is negative 1. Okay, so this one is negative 1. So let me fix this. Sorry, I mistyped this one. So this should be negative 1. This is the red one. So this one is negative 1. So let me just erase. Before we proceed, let's fix the original value. So there's a lot of writing now. So let's erase this one. Okay. So from the start, this one is a negative 1. Okay, so this one is negative 1. Okay, so 2, negative 1, 0, and let me zoom out again. Okay, oops, so let me undo that. Okay, so that's negative 1. So to prove that, we use negative 1 here. Okay, so we use the factor this again, the cofactor. So 0, 0, 3, we have negative 2, we have negative 4, then we have 2. Okay, it's hard to write. Apologize, hard to write. Okay, so this one is the cofactors. So next step is we find the inverse of this one. So the inverse of this one, you remember, so we invert this specific one. So this one is negative 2. Okay, let's rewrite this one again. So this should be negative 2. So this one is negative 2. So this one is 2. So this one is negative 1 for sure. Okay, this one is negative 1. Okay, so another one, so we transpose this one, the 0, 0. So this is negative 3. So this one is negative 2. So this one is negative 4. So this one is 2. So is it finished? No, it's not yet finished. So again, we have a determinant of negative 6. So again, by the formula, so let us review the formula. So the formula for the inverse is this one. So a 1 inverse, okay, equivalent to the 1 over the value of our determinant, then the adjoint a, b, j of a. Okay, so we have already the adjoint, we have already also the value of the determinant. So it's formality, we derive the value. So this one is 1 over negative 6. Okay, this one is 1 over negative 6. So we multiplied by this one. So let's write the matrix. Okay, so let's write the matrix here. So 1, 6. So this one is, if we simplified 1 over 6 times negative 2, this one is 1/3. Okay, so 1, 6, this one is 0. So this one is 1/3 also. This one is 1/3. So this one is 2. So this one is negative 1/3. Okay, so we have 0 again. Then we have negative 4. So this one is negative. So we will yield a positive number. So this one is 2/3. Okay, so next, let me erase this one. Okay, let me fix this. Okay, so 1, 6, negative 1. Okay, so we will have a negative 1 over 6. Okay, then negative 1 over 6 times negative 3. We have a 1/2. Okay, then negative 1, 6 times 2. We have negative 1/3. Okay, whew, that's a lot. So let's check the value. We execute this one. So we will be seeing decimal point in Python. I think Python does not recognize a fraction. So we have 1/3, 0, 1/3. So we're expecting 0.33. So let's execute this one. So shift, enter. Okay. So we have 0, 0, 1/3. So 0.33. So 0.33, 0.33. So 0.33, 0.33. So we have negative 0.33, 0.66. Negative 0.33, 0.66. Okay, so far so good. So positive 16.16. Okay, so I think we have we have an error here. So negative 1.6. Okay, times negative 1, negative 1. It should be positive. Okay, so let me erase this one. So it's still correct. So negative 1, 6. Okay, so we have 0.5, which is 1/2. So right here. Then we have a negative 1/3. Okay, so that is a lot for an inverse. So again, now you appreciate the NumPy library. If you don't have the NumPy library, for sure you will do this, the inverse of a matrix using this method. So remember how tedious this one. Okay, so I want you to review the cofactors. So this, I know you know this one. These are linear algebras only. Okay, you survived calculus. For sure you can do this and study it. Okay, so again, 1/3, 0, 1/3. So 1/3, 0, 1/3. This is negative 1/3. So negative 1/3, 0.66, which is 2/3. So to check again. So we have revised this one. So negative 1/6 multiplied by negative 1 is positive. I thought this is negative, but it's not, it's positive. So 1/6, so negative, so that will be 1/2, then this will be negative. Okay, so that's it for the computation manually versus the computation inside a NumPy. Okay, so for the next lecture, so let's discuss NumPy universal function. So this one is a very tedious lecture. So we have a lot of computations if we try to review this one. So we have matrices. So that's the power of NumPy. So instead of doing these solutions, okay, you only execute 3 lines of code, and the NumPy will compute this one for you. So again, I want you to appreciate NumPy. So without this one, we will result in this one, this tedious computation. So again, I want to see you in the next lecture. So I hope you're doing well with programming in data science. So I hope you're enjoying the subject. So thank you very much.